Okay, let's move on to the first problem where it is related to the wrong binding data type. Let's look at the code that we are seeing on the screen. So you have a class called order processor, and in the order processor class you have a method called accept order, and that is the Azure function. So we have decorated the function name attribute for this particular method, and we have named it accept order. So this is a service bus triggered Azure function. The queue that is being used is the orders queue or orders-queue, and the connection string is specified by this particular connection. So this connection can be configured in your app settings, and the actual connection string will be specified in your app settings through your deployment pipeline. And the message is obtained in this my message variable or argument, and then you have the log as well. And inside the method body, you're just deserializing the message into the order type, and the order type has 4 properties: order ID, customer name, total amount, and order date. So this is the function that is exhibiting a problem. So what is the problem? Everything looks fine, right? The trigger is bound to your queue, the connection string is wired up, locally everything works fine. But then you deploy this function to production environment, and suddenly your function fails mid-flight. The queue is full, the logs whisper unable to convert input type to type X. The function never completes and your retries start stacking up. Here's what's actually happening. The trigger delivers a JSON object, but your binding expects a string. The runtime tries to deserialize it before your code even runs, and it fails. What is the fix? The fix is align your parameter type with your trigger's payload. If your message is JSON, use a POCO or a J object. Add null checks, add fallback deserialization, and when you're dealing with evolving schemas, go with J object. So 2 ways to deal with it. Use the same class type or the POCO type, which is order, which is what is being deserialized over here. The function runtime automatically converts the JSON to this particular type. That's one solution, and the other solution is using J object, because the incoming payload is a JSON payload. So the JSON payload can be serialized into J object as well. So that's another solution for this. So the next time your function suddenly fails with a conversion error, remember the runtime wasn't wrong, but the binding contract was broken. So Azure Functions type binding is a silent contract between you and the runtime. Getting your types wrong will crash your function instantly. But what if your function doesn't crash? It just silently ignores new messages. That's our next trap: schema coupling. When good payloads turn bad. You've got everything humming, your function is stable, the payloads look perfect, and new messages start rolling in from production systems. Until one day, the schema evolves. So this is a schema, second schema, where we have introduced another property called promo code to the order payload or the order class. And this object starts getting pumped into your service bus queue. The function doesn't crash your app, but it stops processing. Messages pile up, logs whisper about deserialization errors, and then silence. You have just met schema coupling. What is the problem? Your trigger and binding assume a fixed schema, which is order. A new field appears in production, and your deserialization says, I don't know what that is. Instead of binding directly to a fixed plain object class or a POCO or J object, validate and then map it manually. That's how you survive when producers evolve faster than consumers. Schema evolution isn't a breaking change, it's a resilience test, and your binding type decides whether you pass. So what you're seeing is a function exhibiting the schema binding problem. It's the same function from our previous example. So we have the service bus trigger, the orders queue is being monitored, and the connection string is specified over here, and the incoming order, which is the JSON payload, is being serialized into the order object, where the type of the order is order ID, customer name, total amount, and order date. So now, what is the problem? Your trigger and binding assume a fixed schema. A new field appears in your production payloads, and your deserializer says, I don't know what that is. Instead of binding directly to a fixed POCO, bind it to J object, validate, and then map manually. That's how you survive when producers evolve faster than consumers. Schema evolution isn't a breaking change. It's a resilience test, and your binding type decides whether you pass. In Azure Functions, binding flexibility is your insurance policy. Schema coupling isn't just a bug, it's a design debt waiting to surface. How do we fix this problem of schema coupling? We instruct the runtime to serialize it to a GeoObject, which is a generic object. We validate the presence of the new fields. Like for example, in this case, we validate the presence of promo code. And based on that, we convert the incoming JSON payload to the appropriate object. So here, the order class is broken down into two versions. One is order v1, which has the initial 4 properties: order ID, customer name, total amount, and order date. And there is an order 2 class which inherits from order v1, and that has the new property called promo code. So in this function, we detect whether we have the new property or not. And if there is a presence of a new property, then we serialize it to order v2, else we serialize it to the order v1 class. And that's how we handle different JSON payloads coming into the service bus triggered queue, service bus queue triggered Azure function. And that is how we solve the problem of schema coupling. Now, schema mismatches can silently block processing, but at least your system tries. Next, we hit the real nightmare: messages that retry endlessly, clogging your queues, which is poison messages. Everything's been running fine, your queue is moving, your functions are processing, and the system feels stable until one message refuses to die. The same message is retried endlessly. Throughput stalls, concurrency drops, and your backlog grows hour by hour. Endless retries is poison message detected. You are watching one bad payload paralyze an entire queue. In production, configure your service bus or event hub with a dead letter queue, or for storage queues, set the max DQ count property in host.json. Add alerts on dead letter queue length, and that's your early warning system. So here we see an Azure function which is triggered by service bus trigger. We are monitoring the same queue, or we are accessing the same queue, which is the orders queue specified in this connection string. The incoming payload is serialized into the order class, and one of the messages fails, and that causes the poison messages to appear in the queue. So how do we solve it? We create one more queue called dead letter queue, and we have a processor service bus triggered function for the dead letter queue, and we read the dead letter queue messages in a different service bus triggered function. So what happens is, whenever there is a poison message detected, service bus itself will push that message because of any exception or something. It will push that message into a dead letter queue, and this function, which is the poison handler, since it is tied to the dead letter queue, it keeps getting triggered whenever there is a message in the dead letter queue. So you can handle based on whatever your scenario is in the dead letter queue, and you can also set up monitoring for the length of the queue or the number of messages in the dead letter queue. So this way, you know how many messages are landing up in the dead letter queue and whether the dead letter triggered Azure function is functioning properly or not. So based on the length of the queue or the number of messages in the queue. That's how you deal with poison messages. Whenever there is an exception thrown by the processing logic of any of the messages in the queue, it causes that message to be pushed to the dead letter queue by the service bus runtime itself. And then when you have another function wired up to receive messages and process messages from the dead letter queue, that's how we handle the poison messages. So enable dead letter queue if you're using service bus queues, or set the max DQ count if you are using Azure storage queues. Add alerts on the dead letter queue length, and add a fallback handler to run when there are messages on the dead letter queue. So that's how we handle poison messages. Poison messages aren't bugs, they are signals. Signals that your validation logic or your schema needs guardrails. Without dead letter queues, one bad record can hold an entire system hostage. Designed for failure, isolate poison messages early. Poison messages can grind your throughput to a halt. But what if your code isn't even flexible enough to retry reliably? That's the danger of over-reliance on bindings. Bindings are beautiful. They make Azure functions feel like magic. No SDKs, no boilerplate code, no connection strings. You drop a few attributes and the data just moves. It's clean, declarative, and perfect until production reality shows. Messages are being processed, logs look normal, but downstream systems are missing data silently. In this case, there's no blob created, no retry, no error. Output bindings failed quietly and you didn't even get a retry. Bindings work great for simple writes, but once you start doing multi-target transactional or conditional logic, they lose transparency and control. You can't add retry policies, you can't log failures, and you can't coordinate across systems. Bindings hide failure modes, no custom retry or backup control if you're targeting multiple destination systems or transactional logic. Bindings are great for simple CRUD. One input, one output. But when you need retries, batching, transactions, or circuit breakers, you need to switch to SDKs. Control beats convenience. So, in this function, you're seeing there's a service bus trigger. So this function is woken up by the service bus trigger whenever a message arrives in the orders queue and specified by this particular service bus connection string. Then you have two output bindings, one for Cosmos and one for Azure Blob. So you're doing some processing. Whenever the message arrives in the service bus queue, you receive that message and you're outputting or sending that message again back to the Cosmos DB and also to the Azure Storage Blob to this particular container, and the order ID is the name of the payload that you're sending it to the blob. So this is a multi-destination output binding. So if there is any issue with this, either of these bindings, there are no errors or no retries. So what's the fix? Whenever we are dealing with multi-destination output bindings, or if we have a lot of transactional logic within our processing code, instead of relying on bindings, we need to rely on SDKs. So here we are using the Azure Storage Blob SDK classes and also the Service Bus client class and also the Cosmos DB class as well. I think in this example we are just using or demonstrating the blob part of the output. So Service Bus client and container client, they are of the types blob container client and Service Bus client. So these are classes from the blob storage SDK and the Service Bus SDK respectively. So they are being initialized whenever this class is being instantiated inside the constructor. This is a method which is the Azure function triggered by the Service Bus trigger for this particular queue, orders queue. This function is named as order archiver. So we are getting the order from the Service Bus queue and then we are trying to serialize it to a variable called payload. And we have this SDK code where we have taken control of writing the processed order back to the Azure Storage Blob. And then we are also sending the archived orders into another queue called archived orders queue using the Service Bus client. So this is how we solve the problem of missed errors or missed retries whenever we are targeting multiple destinations or when we have some complex or transactional logic that we are dealing with inside our code. So that instead of over-relying on the binding itself, we need to take control using the SDKs and write some code to handle this. So bindings are not your architecture. They are your syntax sugar. In production, reliability lives in explicit control, not invisible abstractions. Use bindings for flow, SDKs for control. Bindings make life easy until they silently fail under load. The next culprit is deeper. Your host.json may be misconfigured, choking performance at scale. Your function app isn't broken. It's just slow. Messages are piling up, queues are stretching, and your throughput is half of what it should be. And the culprit? A tiny file most developers never open, host.json. In production, you will see one of two extremes. Either your backlog doesn't drain fast enough, or your downstream system starts screaming under pressure. What is the likely reason? The configuration settings in host.json. So this is a service bus triggered Azure function. There's nothing wrong with it, but the processing is slow and it's processing at half the pace than the expectation. These defaults look safe and they are for development, but in production, a single max concurrent calls of 1 means your service bus trigger can only process one message at a time. The Cosmos DB trigger might pull too many items at once and hit RU thresholds. So what is the fix? So this is the fix. We have specified max concurrent calls as 16. So that means the service bus triggered function can process 16 messages at any point in time instead of one. There's a lock duration specified of maybe 5 minutes, and the prefetch count is specified as 32. So before the service bus triggered Azure function starts processing, there's already 32 messages that are being prefetched and ready for the Azure function to process these messages. And at a time, each Azure function instance can be expanded or scaled to 16 instances so that 16 messages from the service bus can be processed at once. And the Cosmos DB lease is configured. The lease prefix is mentioned as order processor. The maximum items per invocation is 10. The function timeout is specified as 10 minutes for the entire function. So this slows down the load on the downstream, which is the Cosmos DB. Earlier it was 100 max items per invocation, now it is 10. So this slows down the load on the Cosmos DB and makes or scales the service bus to process 16 messages at once instead of processing one message, which it was doing earlier. So now this is a balanced setup. Service bus can prefetch up to 32 messages and process 16 in parallel. Cosmos DB scales gently, pulling 10 documents per invocation with a 2-second delay to avoid throttling. Now, both triggers are tuned for their natural rhythm. Service bus runs fast and parallel, while Cosmos pulls just enough to stay within the RUs. Performance isn't code, it's configuration. Here's the truth. Performance isn't just a code problem, it's configuration. The best developers and architects write functions that scale predictably, not just run successfully. Tune host.json like a throttle, not a constant. Tuning concurrency and batch sizes is critical, but even perfect settings fail if you forget one thing: enabling service bus sessions. Service bus sessions are not enabled, the queue that never empties. Everything looks normal. The queue has messages, the function app is healthy, but nothing is moving. Your queue is frozen and your logs are silent. Active messages 12,487. Function runs 0. No errors, no warnings. You are staring at one of the most confusing traps in Azure functions: sessions without session awareness. If your service bus queue uses sessions, but your function trigger doesn't know that, no message will ever be processed. The function won't even start listening. So what is the likely pitfall? By default, the service bus trigger expects a non-triggered session queue. If your queue requires sessions but your trigger isn't session aware, the listener never locks onto a session and your queue just stalls. So you need to set this property: each session enables to true. By default, it is false. Once you enable sessions required in your service bus queue and you set this each sessions enabled is equal to true, just one line. It tells the runtime to create a session aware listener. Each function instance now logs one session at a time, ensuring ordered message delivery per session. So this is a session aware trigger. It processes messages per session, keeping order intact and ensuring nothing gets lost in parallel chaos. Enable sessions in the trigger. Use service bus session message actions for control. Preserve message order per customer, tenant, or workflow. A single missing property in function.json can freeze your system. But when configured correctly, sessions give you ordered processing, data integrity, and predictable scaling, one logical unit at a time. Small setting, big behavior shift. Always validate session handling before production. Trust, but verify. Before deployment, verify your queue in Service Bus Explorer, confirm sessions are being created and processed in order. Because in distributed systems, the illusion of order can be more dangerous than the chaos itself. Missed sessions can leave messages untouched. But what if your function is awake, yet some partitions are idle while others overloaded? That's the next challenge. Event Hub Partition Alignment. Before we move into the next pitfall, if you found this helpful so far, and if you think I have earned it, hit that like button, subscribe for more Azure and cloud content, and don't forget to tap the bell icon so that you don't miss future videos. Now, let's get back to the 7th pitfall. You scale your Event Hub, you scale your function app, but the math doesn't add up. 10,000 events per second coming in, only 2,000 getting processed. There's a throughput gap of 8,000 events per second. One partition is overloaded, 4 are being idle. Everything's running, but it's not parallelizing. You've hit the silent trap called Partition Misalignment. When you connect Azure functions to an Event Hub, each partition is owned by a function app instance. If you have fewer active function instances than partitions, some partitions simply don't get picked up. Uneven partition ownership, messages stuck in idle partition. So here you're seeing an Azure function which is triggered by the Event Hub trigger, and the events are coming in through this particular consumer group called telemetry processor. And the Event Hub name is telemetry and the connection string is specified over here. By default, each function host can only process one batch per partition. But if your host count or concurrency is lower than your partition count, you're only reading a fraction of the stream. One host, one partition is not equal to 4 partitions. So effective throughput is cut by 75%. So now you have event hubs with 4 partitions, 4 function instances, each owns one lease. Each event hub partition maps to a single consumer at a time. So to process all partitions, you need at least as many concurrent function instances as partitions. So function concurrency should always be greater than or equal to partition count. Use multiple consumer groups if you need parallel pipelines. So now this configuration helps the processor handle higher throughput per partition, but the real alignment happens at deployment type when your function app scale matches your event hub partition count. If multiple workloads need the same event stream, don't share one consumer group. Create dedicated consumer groups to prevent lease contention. In distributed systems, scaling isn't just about more compute, it's about alignment. Event hubs scale by partition. Functions scale by instance. True throughput happens when both move in sync. One partition needs one function app instance. Monitor partition distribution in logs or Azure Monitor. Partition imbalance kills throughput. Even if you balance partitions, Cosmos DB can still bite you with lease conflicts, duplicate or missed events. So that's coming up next. Your function app is consuming the change feed. You think it's working until you notice duplicates, or worse, some events never make it downstream. Your monitored container is being hammered by IO throttling and no one knows why. The change feed is designed exactly for one processing per lease. But when lease management is misconfigured, you get double processing or even missed documents. If multiple function apps or consumer groups share the same lease container, they fight over leases. One app may pick up a document already being processed by another, causing duplicates or missed events. Shared lease container is event collision. What is the fix? Unique lease prefix plus proper RU scaling. So this is the host.json where you configure everything so that there is only one lease named lease. Use a unique lease container prefix for each consumer group. That ensures each processor has its own isolated leases, avoiding collisions. Even with correct leases, insufficient RUs causes throttling. Scale throughput to match your change feed workload. Combine this with a unique lease prefix and your duplicates and misses disappear. Lease control is event control. With Cosmos DB change feed, leases are everything. They are the gatekeepers of your event stream. Mismanaged leases is duplicate storms. Properly isolated leases is predictable, scalable processing. Unique leases is predictable change feed consumption. Leases ensure exactly once processing, but no lease can save you if your function can't even authenticate. That's coming up next, the authentication pitfall. Your function app is deployed, running, and healthy, but every call to Event Hub or storage fails with 401s and 403s. Welcome to the world of authentication pitfalls. Connection blocked at runtime. What's the symptom? Many developers default to connection strings for quick tests, but in production, connection strings may be rotated, revoked, or missing altogether. The result, failed triggers or output writes. Hard-coded or rotated connection strings is runtime failure. So how do we address this? We need to use managed identity and have the Azure function rely on managed identity. Even if you switch to managed identity, you must assign proper roles to the managed identity so that your Azure function has the proper roles that can contact the managed identity, and the managed identity can read or write based on the configuration or the assigned permissions to the third-party services. So you can assign roles to your function app's identity at the right scope. So these are the commands, some of the commands that you can use to assign the roles for the managed identity that your function app uses. So this assigns a role called blob storage contributor to the managed identity. And this command assigns the role called Event Hub's data receiver to the managed identity. And when your function app is deployed, or even after deployment, you can configure the identity to be used by your function app. So the function app uses the managed identity, and the managed identity in turn, which has all these roles, will connect to the respective resources and will have the necessary permissions to talk to those resources. So that's how you solve authentication issues when you're dealing with other Azure services. Authentication issues are invisible until they break production. So managed identity plus RBAC is production grade authentication. Authentication failure is obvious. Your logs scream at you. What's trickier is a silent killer. Binding expression failures when functions don't even trigger. So production grade function code needs to use managed identity. Use managed identity with right roles eliminates connection string headaches. Your functions can authenticate securely, rotate credentials automatically, and follow least privilege principles. So use managed identity, assign proper RBAC roles for the managed identity, verify access before deployment. Authentication issues are invisible until they break production. Managed identity is a modern, secure way to connect. Connection strings are brittle. RBAC is your friend. Test it, verify it, and your functions run without surprise failures. Managed identity plus RBAC is production grade authentication. Authentication failure is obvious. Your logs scream at you. What's trickier is the silent killer. Binding expression failures when functions don't even trigger. So your function app is deployed. This function app is a blob triggered function. Your code is ready, but nothing happens. No trigger fires, no logs appear. The runtime tells you 0 functions found for trigger. Welcome to the world of binding expression failures. This usually happens when a binding expression can't resolve. For example, blob trigger paths like container, name must match the runtime's expected values. If the parameter is missing, misnamed, or too complex, the function never registers. The blob path parameter doesn't resolve, function not discovered. This is the host.json configuration for the function that is exhibiting this pitfall or behavior. The order ID and file name are placeholders. If the blob doesn't match exactly, or if the runtime can't bind the parameters, your function silently disappears from the host. Binding expression mismatch is silent failure. So what is the fix? Simplify paths whenever possible. Use explicit naming like name instead of multiple dynamic segments. Double check that the container and blob names match runtime expectations. Here the runtime correctly resolves name, the function triggers, logs fire, and your processing works reliably. Binding expressions are invisible mistakes. If they fail, your functions won't trigger silently. Keep paths simple, validate placeholders, and watch your functions come alive in production. Binding correctness is equal to trigger reliability. A function that never triggers is easy to spot, but outputs disappearing silently, that's the subtle danger of durability assumptions. Now, I know I've covered a lot, 10 pitfalls in, and your brain might be on fire. So, I want to hear from you. What's the biggest pain point you face when managing triggers and bindings in production? Drop it in the comments. Let's start the conversation. Okay. With that out of the way, let's jump into durability assumptions, because even if your functions trigger, what happens to the output can still bite you if you are not careful. So this function completed successfully. Meanwhile, the blob storage Cosmos containers or the Cosmos containers shows no new items. Your function ran, log says success, but the output disappeared. No retries, no errors, just gone. Welcome to the pitfall of durability assumptions. Many developers assume that an output binding ensures delivery. But bindings are best effort, not transactional. Transient network failures, storage throttling, or SDK errors can silently drop data. Output binding is not equal to guaranteed delivery. Transient failure is silent loss. So, here the function writes to a blob by an output binding. It may silently fail. If storage is throttled, network hiccups occur, or the Azure Functions runtime transiently drops the message. In production, assuming durability can cost you data. Binding writes may silently fail. How do we fix this? We need to rely on SDK code instead of purely relying on the output binding. Use SDK calls with retries and exponential backoff if durability is critical. Combine with monitoring of output targets, blob metrics, Cosmos diagnostics to detect silent failures before they reach your users. Wrap writes in retry logic. Monitor output targets directly. Do not assume bindings are guaranteed. Trust, but verify. Bindings are convenient, but convenience is not reliability. In production, durability requires intention, retry logic, monitoring, and fallback mechanisms. Trust the runtime, but verify delivery. Durability is a design choice, not a binding assumption. Even with retries in place, if you are blind to failures, you won't know anything went wrong. That leads us to a final trap, monitoring blind spots. So, you have your Azure Function Hub dashboard, which shows healthy. Meanwhile, the Event Hub backlog grows. Service bus queues pile up. Your functions appear healthy. Logs show no errors. But your triggers? Some never fired. Some outputs silently failed. Backlogs grow. Users complain. Welcome to monitoring blind spots, the invisible failure. So what's the culprit? You're not being alerted. If you solely rely on function runtime logs, you're missing half the picture. Event hubs, service bus, and Cosmos DB each have their own telemetry. Without correlating it, you cannot tell if triggers fired or bindings succeeded. So logs, that does not mean full observability. Over-reliance on function logs will cause this nightmare. Developers often trust logs alone. Functions report success, but the underlying event may never have been processed, or output may have failed silently. That's why production-grade observability requires end-to-end correlation. Single source of truth is incomplete. So, you need to stitch up the diagnostic settings of Event Hubs, Service Bus, and Cosmos DB through the portal, enable diagnostic settings, send them to Application Insights or Azure Logs Analytics. Once you have sent these metrics or logs to Log Analytics, you can correlate via the operation ID or correlation ID. You can set alerts, you can monitor the queue length, backlog, or failed event count. Trigger alerts via email, Teams, or PagerDuty. By sending platform telemetry to application insights and correlating with your function logs, you get a complete picture which triggers fired, which events succeeded, and which backlogs are growing. Attach an operational ID or correlation ID to each batch or event. This lets you trace it across triggers, outputs, and telemetry, giving you end-to-end observability, not just isolated logs. So enable diagnostics on triggers, correlate logs via operational ID or correlation ID, set alerts for backlogs and failures. What you don't see will hurt you. Monitoring blind spots are invisible until they become outages. Production grade observability requires all layers: runtime, triggers, bindings, and outputs. Only then can you detect, alert, and resolve issues before users notice. End-to-end monitoring is production safety. Now you know exactly how triggers and bindings work and how to configure them right the first time. No more silent failures, no more function didn't start mysteries. Just fast, reliable, serverless automation, the way Azure functions were meant to be used. But knowing what can go wrong is only half the story. The next step is taking full control, configuring your functions for production-grade observability and throughput and scale. In the next video, we'll dive into application insights configuration, metrics for each trigger and binding, and how to control throughput and concurrency so your functions scale reliably without overwhelming downstream services. If you thought avoiding pitfalls was powerful, wait until you see how configuration gives you mastery over your serverless apps. Click right here to watch the next video and take your Azure functions to the next level. See you in the next one.